Exactly. It's like what I stressed to them. I emailed the parent back. It's like, let me stress to you that this is just the start of the
Let's
third
just
night.
hope that they have canned food drop.
Oh.
I mean, I don't know.
I'll bring stuff in even if we don't.
Anyone else in here.
Yeah, can we just bring cans to you
Yeah,
and
we,
take to the church?
we can fill up the boxes in town. Oh, yeah, yeah.
We just box outside.
Okay.
Let's
All right, so on this, we had left off on number 51.
I thought we finished 51 because he was going over. He was like.
We got
Part B, I never got to see. It's you guys were asking about Part C, and I think you guys are right on how to figure it out. But we got to make sure that you are right. So in this case, Part C in number 51 says, using the acceleration from Part B, how long does it take to pull the people up to the helicopter? Assume the people are initially at rest. So everything's totally changed now. Oh, man.
Wait,
Never finished B.
I was gonna say, where's it? We have the acceleration for it.
We have it.
You
It
wrote
was like
it.
we took that and put it over 120 kilograms.
Oh no, we didn't
Right.
finish B. You were just getting to the end and they called us
Oh, I did not. I did not. I don't know.
You were
Can
just
we-
getting ready
Here
to
we go.
explain how you put the...
Can we just restart on B so then
Gravity in
we
there.
got a good grasp of what's going
Yeah,
on for it?
restore.
Okay, yeah, I'll give you a run through again. So pretty much all I've done here is I've just drawn this free body diagram. It's literally all I've done. And on the free body diagram, we know that the force being applied by the winch is 1,200 newtons. But then we have to worry about weight because it's going in the opposite direction of the force being applied. And we did the math on that because the people are 120 kilograms. And you have acceleration and gravity when it comes to weight. So we found that the force of weight was 1,177.2 newtons.
What problem number is this?
It's 51.
Wow, I got 10.
You didn't put gravity in
No,
there. Good job, Thomas.
I had the same thing for a while, Thomas.
So in this, here's the thing, is what we really care about when you're wanting to find this acceleration going on here. We really need the net force. And remember that net force is the summation of the forces. So that would be force applied plus weight, which will be equal to 1,200 newtons plus a negative 1,177.2 newtons. Why is that negative?
Because you're subtracting it.
Because it's the force
It's
against
down.
the...
Yeah. Like,
Because it's down, it's going in the opposite direction. So we have to have an opposite sign.
Okay.
So I chose up as positive because that's the direction we're trying to move. So in this case,
What did you add together then?
the forces. Force applied and weight.
This is...
is that C or B?
This is B. I marked out C.
Okay.
I never finished B.
Okay.
So in this case, we do this. And we get a net force of 22.8 newtons. And that's good because we have magnitude, but the most important part of it is the direction. It's positive, so it tells me that the cable is moving up. We're actually pulling the people up. That's a good thing. Now in this, we're trying to find acceleration. And in that, we're going to use the equation force equals mass times acceleration. So the net force, as the force we're going to use the mass of the people that's there, that 120 kilograms, to find that acceleration. So acceleration is equal to the net force divided by the mass.
Okay, so...
So the net force we calculated to be 22.8 22.8 newtons divided by the mass, which is 120 kilograms. So when we do that, we'll end up with 0.19 meters per second squared.
That's faster than 1 second. Oh no. Okay, that was a bomb moment there. That was a bomb moment. I was thinking about C and finding how fast it was going, and I was like, hold on, how'd that happen?
I'm not understanding how you got the FAP and the weight. Is the
The force
FAP the
applied.
120 kilograms?
No, that came from the problem. That they told you the winch applies a force of 1,200 newtons.
Oh, okay.
That's okay. I know newtons is like it's broke down into other things, but it's actually like represented by the N. As far as getting the units for the answer, can you go?
Yeah. Okay, so in this case,
Didn't you say like
unit-wise, you have
equals
newtons divided by kilogram. Well, you can break newtons down. Newtons is equal to kilogram times meters all over seconds squared, and that's still going to be divided by the kilograms. So in this case, kilograms cancel out.
Now, is acceleration always going to be meters per
Freshman
second
9-2
squared?
to the auditorium
Like
for
the unit that
pictures.
goes with it as far as what we're doing?
Yes, and like, I could be wrong, but I think there's a couple problems in the book that we'll solve and run through that we will not end up with meters per second squared because our units are different. And I look and I say, there really isn't a reason to convert it, so let's not convert it, let's just leave it as it is. But
Well, no,
the majority of it, what you're looking at is what you'll see. Can I help you?
Miss Sam will sit you down here. She said you know the password to the Wi-Fi.
That should have its own, it should automatically connect.
Okay, well, take that.
That's it?
Yeah.
The side eye.
Give me that.
I think I got C.
Drops.
I think I got C.
I can't remember how to get C. I had it.
Let's-
You divide 0.19 meters per second squared by 12 meters. How do you know that?
by 12 meters.
Well, yeah, because that's the distance.
You want to find how many seconds it takes
Oh,
to
okay,
travel
yeah.
with 12
I am
meters.
like
So it's going to be 12 divided by
Yeah.
0.19.
12
Yeah.
divided.
Good Lord.
It
That's
takes
big
about a
number.
minute to get there.
A minute, 3 seconds.
Have y'all seen that video of the woman? She's like getting attached to the helicopter or whatever, and they're like flying her out. But like where the helicopter's at, the wind is so high, and so she starts spinning. And they can't get her to stop, and so they're like raising her and lowering her. She's just like rolling around. Oh, it's so awful, but it's so funny.
You tried turning it off there, man.
That fixes it. I'm sorry, I
Did you
couldn't
put
help
it in rice?
Don't put it in your eyes. It's not gonna fix the password issue.
Might fix a water issue.
Oh, wow.
Hello.
Hi.
Take that.
No,
Hello
Take
again.
that.
it's not tech day.
Take that.
I don't need him yet. I need Olivia. Can I, oh, I missed a phone call from the board's office. We're not read, that's for sure, because we'll never be read again.
Oh.
Olivia,
Huh.
do you care to shout
I
out your
have no
telephone
idea.
number?
That would be,
923
Hold on.
Let me
923
563
Okay, so,
5630.
30.
I'm gonna message you what he sent to me. I already messaged it to Mom.
Okay.
I'm sorry, Mr. Kevin.
you're totally fine.
No, if I want to do
I
that,
did
I'd
want
already
to.
done.
I do think that I set it up correctly, but I haven't done a test run yet.
I believe in you. You got this.
Take that.
I have no faith in me. I have no faith, technology-wise, these guys do.
All right, C. So using the acceleration from part B, how long does it take to pull the people up to the helicopter as soon as the people are initially at rest? So, we're going to look at doing what we've always done. We're trying to find time. So, this all look very familiar.
Oh my god.
I have not read
Why are
this.
y'all crying?
Why would you use that one instead of
The easy one.
And what's y'all's definition of the easy one?
the T,
The
equals a,
distance over time. Isn't that?
What?
I don't know, I failed the
Just
quiz.
do it.
Huh?
Distance is equal to rate times time? Because that's not a physics equation. That's why.
Does it work though?
But it works.
If you want to go with that, you go with that. And that goes back to what we just said a little bit ago.
You're gonna count off for me doing that?
No, I ain't gonna count off, but you better make sure you're right.
Dun, dun, dun.
You're trying to look and say it should work. Should and will is two totally different things. Because with this equation, I can look and say that my initial position is 0, so it's gone. I can also look at this and say my initial velocity, I started at rest, so it's 0, so now that quantity's gone. So now I'm left with a final position equals 1/2 times acceleration times time squared. I'm trying to find time.
yeah, this
So I can look and say that time is equal to the square root of
I looked at what I
2
did,
times
and
y
I
final.
2 times.
You gotta get rid of the 1/2. So you gotta multiply both sides by 2.
Oh.
So
So if
then,
I don't work
2
it out
times y
exactly
final.
like this, you're gonna count off on my quiz.
oh god,
if you get the right answer, no.
Okay.
I'm gonna be very intrigued to see how you got the right answer if you don't work
I'm
it out.
waiting for us to get the right answer right now.
So times 2, and we're going to divide by acceleration, which we calculated that out, so it's going to be the square root of 2 times y final, which we know is 12 meters, and I got that from the picture. That's where that came from. And that's going to be divided by the acceleration, which we calculated, be 0.19 meters per second squared.
Where do you get that to?
You gotta get the 1/2 over to the side, so you multiply both sides by 2. Square root 2 times 12 divided by. What'd you get?
126.
7.9472.
I got 11.2390.
I've probably done that wrong.
Yeah.
You gotta take the square root of 126.
What?
No,
Wait,
you
what
get
was?
11.2390 seconds.
Okay.
So did your equation work?
Why do you have to go through all that to find it though, when you could just take the meters and divide it by meters per second to get the second?
what?
Like if you take meters, you divide that by meters per second squared, you're left with the second.
Squared. Squared. You're not left with seconds.
So then,
So then couldn't you take that
Square
and-
root.
If you're gonna start trying to do that and just come up, Matt, and just try to make things fit, it's not gonna go well for you in this class. You have to know your mathematical formulas, how they apply, and you can't just wish them around and mix them up and say, oh, well, this should work.
I'm just trying it, okay?
Quiz.
I'm looking at you and telling you what does work. You're trying to come up with something and say, well, this should work, shouldn't it?
Maddie, just be glad you didn't have to take a quiz.
God.
Questions on 51?
No, sir.
I don't get so. Is there no way we could have used the time equals velocity final minus velocity initial over A?
You're gonna have to find velocity final.
Oh, okay. That's what I was thinking.
That's why that one doesn't work. Because you have two variables stuck in there.
So force is Newton.
The unit is newtons, yes.
Okay. Progress.
That's
That
so
ain't
positive. All right, so here is the dandy of problems.
That wasn't the dandy.
Is this one hard?
This one makes you think.
I can't think.
Not bad.
It makes you think on a level that you've never thought of before.
I don't
It's not
know.
processing
I thought it was
everything.
hard this morning.
Number 52. This is it's a dandy.
Freshman 9-3 to the auditorium for pictures.
Okay, so in this case, what force would a scale in an elevator on Earth exert on a 53 kilogram person standing on it during the following situation? So I have a person and I have a mass of 53 kilograms. So before I go any further in this, we have to think, and this is where I want you to think, what is the one equation that I taught you in this chapter we keep using dealing with force?
Max times acceleration.
Force equals mass times acceleration. So in this is what you're going to see. It's in terms of acceleration. Remember what acceleration is. It's a change in velocity over a change in time. If the velocity, or the speed, if it's not changing and it remains constant, what is your acceleration?
Gravity?
Gravity.
0.
0, thank you. In this case, though, you're also right.
Really?
Because what's happened? We have weight. So we have to take into account gravity. But now, think about whenever you've stood on an elevator before. So you're standing on the elevator, you press the button to move up a floor. The door closes. Do you feel anything different before the elevator moves?
No.
No. Whenever the elevator starts going up, do you feel something different?
No.
Yes. You feel a weight. You feel your weight increase. Why did your weight increase?
Just something to
Push
push
it,
it
you're going forward.
I guess
Because
so.
here's the elevator that's moved and accelerated upward.
And force is
Okay, what do
pushing
you
down.
want to do? You're wanting to go down. So here it is, you're wanting to go down. You have gravity normally pushing you down. And the elevator comes up.
That makes so much more sense.
Just because you did this whole thing.
Yeah.
So you're looking at two forces opposing each other in that moment. What creates and what makes you feel the change on the anatomy level in your body? A force being applied. Because the elevator wants to go up, it goes up, and you're touching it, so you feel it. It pushes you up. Now, about a second into that, the elevator's moving at a constant velocity. So now you feel like you did when you were just normally standing there, because it's no longer accelerating. But what happens whenever it gets right there at the door, at the floor you're wanting to get to?
It feels like a
It
draw.
bobbles a
It
little
slows down. So now the elevator's decelerated. So it's slowed down. Whenever it does that, you feel a little more
Like,
weightless, like, oh. I feel like I just dropped 30 pounds. Why can this not be my mass? The joke there, because the mass didn't change.
Yeah.
The weight did, but the mass didn't.
Da-da.
So smart.
Okay, so in that, you feel less force on you. Why? Because it's slowed down. So the acceleration's going in the opposite direction. There's a force happening on the opposite direction. To where your acceleration's changed in the opposite direction now. That's what this problem is all about. Putting you in a scenario where you have to think the whole time of what is happening. So let's go into number 52. So we got a 53 kilogram person that is on a scale in an elevator. So in this, let's look at A. So we know our mass. We're going to try to find force. The mass, does it change ever? No. What's changing is acceleration. So every one of these scenarios, we are looking strictly at the acceleration. Okay? So A, the elevator moves up at a constant speed. So the elevator is moving upward at a constant speed. You're standing on a scale. What are we looking at acceleration-wise?
Gravity.
Just gravity. Why is it just gravity?
Because you're standing on it and it's waiting.
It's the only force we can
Because that's what we're just looking at. The elevator is at a constant speed, so there's no acceleration acting on us from the elevator. The only thing acting on us right now is
Because we're
gravity.
not.
So gravity can be considered a 0 point. Like I think about
Need a
it's like
custodian in the office, please.
It's like the
On a
initial.
scale.
Custodian in the office.
put something on it and make that the 0, so gravity would be the 0.
We can do that, but on this case, the scale has not done this. So we still have to account for this.
Wait, so why would it only be gravity? Because we're not moving? Because we're not
You're moving, but you're moving at a constant velocity. Remember, what's acceleration? A change in velocity over a change in time. If I'm moving at 4 meters per second, and all I did was move at 4 meters per second for 1 second, final velocity, 4 meters per second, minus initial velocity, 4 meters per second, is 4 meters per second minus 4 meters per second is 0. The acceleration is 0. There is no additional acceleration coming from the elevator. So now we have to choose something here though. What direction are we making positive and what direction are we making negative?
We're making the elevator positive and gravity negative. Gravity and earth.
You can't make the elevator negative because every
They're
scenario has an
going
acceleration going in a different direction.
They're
I
going
said
up positive.
that. I said the elevator positive.
You can't make the elevator positive.
Then let the elevator.
You're choosing a direction. Is up positive or
Yeah,
down positive?
up.
Is positive.
Okay, so up is positive.
That's what I. That's what
No, you said elevator is positive.
Oh my
That's not
god.
up. Elevators
When the
go up and
elevator
down.
goes
An
up.
elevator can go down?
When
You can't
the
do that
elevator
because
goes
now
up.
you're changing scenario
Okay.
dead straight.
Okay, now
You
listen.
have to choose a direction and
When
stay definite
the
to it.
elevator goes up. That is positive.
You
Is that
can't
better?
choose it like that because you're going to flip here. Halfway through this.
What are you?
Halfway through, Maddie, open your book and read the problem. Halfway through, it flips. It goes from moving up to moving down. The elevator's going to go in 2 directions. You can't determine that the elevator is positive because it's going to go up and down. That's why you choose up is positive or down is positive.
Okay, up.
So up positive, down is negative.
This is what I said, and you
So
started
in
going
this,
off.
that is not what you said.
I said.
You said gravity is negative and elevator is positive.
And then I said when the elevator goes up.
Oh my
But the elevator goes up and down.
You literally And then, but when I said when it goes up, it's positive. I'm wrong.
The elevator's positive.
You said the elevator's positive.
Whatever. We were talking about the elevator going up, so I had
Maddie,
assumed.
you're fighting a losing battle
I
again.
had
Let
assumed
it
you
go.
were like, oh, she means when the elevator goes up because you were doing this whole thing.
You can't assume. When you choose your reference point, you have to walk the line with the reference point.
You always do this with me. Always. Chemistry, anatomy, biology, anything, you will pick this fight with me. just to get a reaction out of me.
So in this case, we got gravity, which is 9.81 meters per second squared. And in this, gravity is going downward, so down is negative, so that means gravity is negative. This is the reason why it is so important to label this out. Because if I give you a problem like this, you have to walk the line with your reference point you chose.
Why would gravity be negative?
Because
Because gravity is always pointing down directly to the core of the Earth.
Can we draw like a bit of like a free body
That'd be
diagram
nice.
to kind of like get everything pieced together?
Sure.
I always draw a little man, and I name him Mr. Hall.
While we're at it, why don't we draw a box and whisker plot?
Okay, that's
Oh,
what I'm
that's
too
too
far.
hard. No.
Alright, so we got force of gravity going down.
Do a scatter plot though, Thomas.
I will look at you and tell you, yes, you have a normal force going upward. That's what's stopping us from falling through the elevator. But in this, we're not worried about that because what's the scale built to read? The scale is built to read this force of gravity. You have to know what you're looking at. That's why I love this problem. There's so much thought behind it. It's not a lot of calculation, it's a lot of thought.
So technically when we weigh ourselves, that's not really our weight, it's just weighing gravity.
That's our.
No, it is your weight. It's taking gravity, pushing down on you, and finding that force.
So gravity is making me appear a lot fatter than I am.
No,
And
gravity
telling
is
mass
just your
and
weight.
weight is something different.
So is it a mass measurer or a weight measurer?
It's weight.
So do
Wait,
we have
so
mass measurers
is-
out there?
You
Is
do have
weight,
mass.
mass, and
Hey, where can I
gravity?
get one of those? I want to be skinny.
Yes.
Yes, weight is mass and gravity together. They're very
Why do you
expensive.
have to say it like that?
Really?
You could just
They
say
actually
yes.
make those?
I know.
So,
why
in
is
this-
it Connor here? Connor is the one that takes this.
No, Connor would have been added into it.
So we're going to find force is equal to mass times acceleration. The mass is 53 kilograms times the acceleration, which is negative 9.81 meters per second squared.
Will we get newtons out of this?
That's a big number.
You tell me,
I think we will.
why would you get newton
Because
out
it's
of
got kilograms and meters per year.
Squared.
it? Look at you. I'm so proud, Christy.
This is, I'm actually.
So negative 519.93 newtons is what the scale will show. Who would have known? All it took was my hand and my fingers pushing on this.
You just gotta give me.
It's so much
I
easier
need
to,
visual.
to see. Like,
Apparently
when
that
you
didn't
have,
work
like,
for me,
information and
'cause-
seeing it. It makes it easier.
That's all I
the
hear is
thought
like
process.
gibberish.
Okay.
This is force, right?
Are you mad at me, Mr. Hall?
No. So let's look at B.
Go shine.
First, maybe you can't even take that on test.
I ain't mad.
He's mad. He's aggravated.
I ain't aggravated. I'm waiting on the chemistry parents to start calling. That's what I'm waiting for.
Mom,
Did
mad at
they
me.
do that bad? Like worse than we did?
Oh, we.
Which quiz?
We done
I
bad.
know that on our first one we did pretty okay.
No, we didn't.
No, second period.
Yeah. The second, I don't know.
Okay.
Something about that class.
Now B.
Really.
B says it slows at 2.0 meters per second squared, moving upward. So the elevator is moving up. and then it starts to slow down.
Moving.
So that'd be force applied would be the number
I
that you
can't
just
say
read off,
just the
right?
elevators, but the elevator is moving up. Positive. Up.
The elevator is moving up. What is it?
The number you just read off, that would be force applied, right? Because it's causing it to slow down.
It's the acceleration. They're not giving us the forces. They're making it easier on us and just giving us the accelerations so we can deal with
So
the difference in those.
Anytime we're given like a time, that's usually acceleration.
Meters per
Like,
second.
Yeah, like
So,
you just said.
Meters per second squared is acceleration.
What did you just say the number was?
The 2.0 meters per second
Okay, then yeah.
squared.
So where this is slowing down and we establish our positive is going upward, would this be a negative acceleration?
No,
Hold
when
on.
it's going up. And it's
No,
all-
but it's
all
slowing
going-
down.
This is,
It's not coming down though, it's just slowing down as
I'm
it goes
going
up.
up.
it would be acceleration applied to slow it down.
Okay, so this is
it
the
would
thing.
be-
So that would be the same as the 3 if I do that car, just slow it down.
Elevator is being forced to slow down. But what's happening in terms of us? We still have that that velocity that was going up. And now it's bringing the elevator down. So for us, in terms of us, this acceleration's opposite of the motion. This is where we feel like we lost weight. We feel more weight gone away.
Rejuvenated.
So it would be negative.
It's going to be opposite of gravity. This will be positive.
So
Yeah,
it's
because
not
gravity's
going to be
negative.
negative, it's just slow
Well-
it down.
But if gravity
Where
was
we
positive,
establish
we would
gravity
make
as a
it
It's
negative.
not
Yeah.
like you're going
Yes.
down.
But where we're,
So like if
It's not
gravity's
like you're
pulling
going
down,
down, you're
this
just
would be
slowing
like
down.
pushing up to like slow it. As
oh,
it
okay,
goes
I got you now. I got you.
Yes.
Gracias.
Okay, so in
You haven't
this,
changed
the
direction.
acceleration
Oh,
is gravity,
Mhm.
but we also have the other acceleration to take into place. So it's gravity plus the 2.0 meters per second squared.
Which would be 7.81 meters per second.
Negative.
Yeah.
Hold on, before we jump into this, let me think.
Because the initial acceleration is slowed.
No. This will be negative.
I told you.
Because elevators slowed down, so we were traveling at the same rate. We're still traveling at the same rate, but the elevator
it's
now is
slowed
slowing down. So we are
It's
pushing
like that
down more.
problem with the car where it was
It's opposite
slowing
effect what I
down.
said.
So,
It's
You
slowing
feel
down at a
more weight.
rate.
You feel a jolt.
Okay, so may I ask
so I was right.
What?
So is it slowing down at a rate of 2.0 meters per second squared?
Sydney Cochran reports
Yes.
to Digital Learning Center. Sydney Cochran reports to Digital Learning Center, please.
So we'll get negative 11.81 meters per second squared as the acceleration. So the force we'll get is 53 kilograms times the negative 11.81 meters per second squared is equal to negative 625.93 newtons.
Is that 11.81?
93. Oh, 11.81, yes, sorry. Question. I know this one's hard. I know this is a lot of thinking, and you've never thought like this before.
So, well, maybe as far as whenever you get comes time to taking the quiz, would this be like a problem that would be on the quiz, or would it be like what? Or is this like the show you the hard one and then it's actually easier than what it is?
You were in chemistry.
Once
When
you
did I
learn
ever
it-
tell you what's on my quiz?
No,
Once
I just
you
meant like to
learn
that
it, don't
caliber,
forget
like of
it.
the multiple steps, like that, like
Oh,
You
on the
know,
quiz.
Once you learn it, don't forget it. All's fair in game.
I'm just asking
And
if
he
they
was
want stuff on
number
computer.
one.
Well,
That's the one thing I remember from my commercial. He was number one.
What was his name?